Hey guys, good day. I'm Christian Davitanong from ECE-37 and today we're going to summarize the architecture all access modern CPU architecture part 1 and 2 videos. So, first on our list, the CPU or central processing unit. It is often called as the brain of the computer. CPUs are a general purpose flexible architecture that take in a stream of instructions from all types of workloads and compute or process information based on those instructions. Next, the Moore's Law. Moore's Law is based on the observed trend showing that we can double the number of transistors per unit area about every 2 years. This simple law drives tremendous innovation, making what was once thought to be impossible not only possible but also cheaper over time. Then we tackled about the CPU architecture history. First, from the digital computer from 1946 covered 1,800 square feet. In the late 1940s, John von Neumann popularized a new kind of computer architecture that simplified computer design and programming. In the 1950s, semiconductor-based transistors started to hit the market. Then, in 1959, Robert Noyce patented the first monolithic integrated circuit. By 1968, Robert Noyce teamed up with colleague Gordon Moore to found Intel, which was short for Integrated Electronics. But in 1971, they unveiled the Intel 4004. In 1972, Intel released the first 8-bit microprocessor, the Intel 8008. But in 1974, its successor was released, known as the Intel 8008, 8080. In 1978, the 16-bit 8086 was released. The Intel 8086 with its x86 instruction set architecture became the foundation for modern CPU designs that we still use today. The computing abstraction layers. Using transistors as switches and connecting the output of one to the input of another, we can build a variety of logic circuits or functional blocks. The instruction set architecture or ISA describes the memory model supported data types, registers, and behaviors of machine code. The ISA acts like a sort of bridge between software and hardware. Key building blocks in a CPU. A microarchitecture is an implementation or specific design of an instruction set architecture. The first step is called the fetch stage and the second is the decode stage. The pipeline depth. In general, the more pipeline stages you have, the faster each stage can run, and the more stages are being done in parallel. The branch prediction. When we see we have gone down with the wrong path, we can update or refine that prediction with what the right path was. Then, the next time you see that address, the branch predictor can tell us to go to a different address. The speculative execution. When a microprocessor executes newer instructions than a branch without knowing if that branch is taken or not, it is referred to as speculative execution. The microprocessor front-end predict and fetch. To optimize both power and performance, many adjacent instructions are fetched at the same time, which are handed off to the decoders. The microprocessor front-end decode, where the program's instructions are decoded into the microarchitecture's internal operations, which are called micro operations or UOPs for short. Then, the superscalar execution. This is the modern microprocessors now implement many ALUs, and when those ALUs can operate in parallel, this is called superscalar execution. All modern microprocessors are superscalar. Also, we talked about the out of order. In basic microarchitecture, the UOPs are executed in program order. which is called in-order execution. However, in order to provide the best performance and energy efficiency, executing them in out of order is actually better, allowing code to execute faster as we remove unnecessary wait times. And lastly, the CPU backend. The backend refers to parts of a computer application or a program's code that allow it to operate and that cannot be accessed by a user. Most data and operating syntax are stored and accessed in the backend of a computer system. Typically, the code is comprised of one or more programming languages. And that's the end of the video. Goodbye.